when I dissolve ions in solution, that also allows me to have the possibility to conduct electricity. And so we just saw different ionic substances have different solubilities, but ultimately, the more ions I can get to dissolve, the more electricity I can conduct. Right? So the way this works is, if I take a solid, put it in water, the water separates the ions, surrounds them. Now that the ions are separated, they have the ability to move around in solution. This is called an electrolyte because it can conduct electricity. And so the way that works is, if I, it's hard to see because it's kind of small, but if I take a light bulb and have a wire putting electricity into that light bulb, but for the electricity to make it through the light bulb, it has to come down here, pass through the water, and then come back up through. So to complete the circuit, the electricity has to go through the water. So on one side of the water, I've got a positive electrode, and on the other side I have a negative electrode. So as long as I have ions in solution where the negative ions can all move to the positive electrode, and the positive ions can move to the opposite side, I can conduct that electricity and light up the light bulb. Conversely, if I put in something in water that doesn't have charges, like a non-electrolyte, like sugar, sugar molecules stick together. They have to stick together to make their noble gas configuration. They're not stable if they break up and create unstable formal charges. So when I dissolve sugar in water, it just stays. The molecules stick together. So that's a key difference between dissolving an ionic substance and dissolving a molecular substance. If it's just dissolving, that means there's no chemical reaction. So if I'm just dissolving an ionic substance, the ions break apart. I break the ionic bonds, I get the charges that can conduct electricity by flowing in opposite directions in solution. If I dissolve a molecular substance, which is a non-electrolyte, if it's not an acid or a base, it's not undergoing a chemical reaction, it's just a molecule, the molecules will separate from one another, but the molecule itself won't break apart into pieces. So initially I'll have, these, in the solid, I'll have these sugar molecules packed together, attracting one another through hydrogen bonds. When I dissolve that in water, the sugar molecules separate, but the sugar molecules remain intact. They don't break apart as individual molecules. And so the sugar just doesn't form any charges. So when I connect the same setup, I can't conduct any electricity through the solution. So this also means that water will not conduct electricity, which is contrary to popular belief. So if you're worried about getting electrocuted when you're standing in water, it's not because the water conducts electricity, it's because there are ions in the water that conduct electricity. You need to have charges in water. So if you have tap water, or there's salt from sweat, which there pretty much always is, on your skin, and that dissolves in the water, then that water can conduct electricity because there are charged particles in it. If you have absolutely pure water with no ions, it will not be able to conduct electricity, and you won't be able to get electrocuted by that. So there's a visual for this one that's nice. So here we have water. We're going to add some salt. Shake in some salt. And I can use this to measure the conductivity. See the little yellow lines? It tells me that's bright. So if I add more salt, it gets brighter and brighter. Right, so the idea is, as I add the salt, I get more positive and more negative charges, and they can flow in solution. Right? So down here in solution, the positive ions are flowing toward this side, the negative ions are flowing toward that side, and that motion or flowing of the charges conducts electricity. The more salt I put in, the brighter it gets. If I switch to sugar, and I add the sugar, there's no change in how bright it is, because the sugar is not producing charges in solution. So an electrolyte is something that produces charge in solution. What if I start to evaporate the water? How will that affect the conductivity? Well, if I evaporate some of the water, it should get brighter and brighter and brighter. Right now, because I'm not adding more salt, but I have a higher concentration of the salt. I have more salt in a given amount of volume, and so I have more ability for those salt ions to move in opposite directions and conduct a charge. So conductivity is based on how much charge I have and how little space that charge has to move around it. So this also has a nice feature. It allows us to see the charges. So when I add, it won't let me add anymore. It's empty. So when I add the salt, the ions separate. That just shows illustrating the fact that the ionic bonds break, the positive and negative ions separate, and they move around freely, surrounded by water molecules. If I evaporate some of the water, the concentration increases because now they have less space to spread out in, so I can conduct more electricity. If I add the sugar molecules stay intact. Right? So the sugar molecules separate from one another, but each individual molecule with a certain number of carbon, hydrogen, and oxygen does not break apart. That's why it's a non-electrolyte. Right? So each individual C12H22O11 has no charge. It's not breaking apart, so it's not going to aid in the conductivity of the solution. So this is like similar to what we already saw. Any questions about that? All right. So strong electrolytes, ones that produce lots of charge, are water-soluble ionic compounds. So any compound that when I just put it in water will actually dissolve. For every one of these, I will get a stoichiometric amount of positive and negative ions. The more of this I put in, the more ions I get, the more I can conduct electricity. Other strong electrolytes, strong acids. Strong acids are not technically salts. They're not ionic compounds. They're molecular compounds, but they're unstable. So when I put this in water, it will react with water. The H plus will go to the water, produce H3O plus, and the Cl minus will be free. So I'm producing charges. I didn't have the charges to begin with. This is different. Here I already had charged particles. I'm just allowing the charges to separate. Here it's not charged, but because it's reactive and the water picks that H plus up, and this should actually be H3O plus. I get that H3O plus and the Cl minus. I'm producing charges. Since it's a strong acid, for every one of these I put in, I create charges. So that makes it also a strong electrolyte because I'm creating lots of charge for every molecule I put in. And the strong bases that have an OH attracted to a metal, those are really no different from water-soluble salts, because when they already have charges, positive and negative. And so when they dissolve, just the charges are separating. I create the ability for the charges to flow in solution so I can conduct electricity. Weak electrolytes are similar, but the light is not as bright here. Right, so if I put a mole of a strong electrolyte in solution, I'll get lots of charge. I'll get a mole of charge. I'll get a very bright light. If I put a mole of a weak electrolyte in solution, like a weak acid or a weak base, then I get usually much less than a mole of charges, because only some of the molecules will break up. Right? So a weak acid is one where when I put it in water, most of the molecules will remain intact, which means they won't have charges. Those ones won't conduct electricity, but a few of them will put an H plus onto a water, creating H3O plus, and then when this molecule loses that H plus, it'll be charged, and so I'll create a few charges. So I'll be able to conduct a little bit of electricity. Same thing for a weak base. If it's neutral to begin with, and the molecule remains intact, which many of them will. If it's weak, most of them won't react. That won't conduct any electricity. But the few that do react will pick an H plus up, become positively charged. The remaining water will be OH minus, and I'll create a few charges, so I'll conduct a little bit of electricity. So again, if you remember what we said about the double arrow, that means you have an equilibrium. Right? So when I have a weak substance, it can react with water to produce some charges, but then those charges are not as stable. What's the difference between a weak and a strong? If this were a strong substance, when it reacts with water, it reacts almost 100% because the resulting products are so stable, even when they collide, they don't really go back very much. And so I get lots of charges, and those charges build up, I can conduct more electricity. But a weak substance, when it collides with water and creates these charges, these are still pretty unstable. So when they collide, the OH minus picks the H plus back up, and I reproduce my reactants. So it can go back and forth and back and forth. And the less stable the products are, the more often they collide and produce the reactants. So most of the molecules will be in this form where they're not charged, and I won't be able to conduct much electricity. So let's just check out this video here. Does a good job of illustrating this.
An electrolyte is a substance that, when dissolved in water, results in a solution that can conduct electricity. The light bulb will light if a substance is an electrolyte.
Get rid of this guy's voice so I can go through this a lot quicker. So
Sodium chloride, NaCl, is a soluble salt that is assumed to completely dissociate into ions. NaCl is a strong electrolyte when dissolved in water. The solution contains a large number of ions, and the light bulb with the positive and negative ions of this.
A nice little video of them showing you.
Polar water molecules interact with the positive and negative ions of the salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between the water and the salt ions causes the salt to break apart or dissolve in water.
If the salt didn't dissolve, if it stayed in the form of NaCl,
Hydrofluoric acid, HF, is a weak acid which only part
conduct electricity.
Dissolve in water.
If these ions stuck together, there's no conductivity. They have to be separated and be able to flow in opposite directions for the electricity to be conducted. So another example is the HF. So when I put HF in water, bubble that in there, I see a little conductivity. So
at equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ion, F-.
This isn't totally correct because when the H...
Methanol, CH3OH, does not dissociate into ions when dissolved in...
It's not totally free. Just pause this at this moment. Right. So what we have here is the HF molecule. Not totally correct, because when that breaks, it's not just going to fall apart. It requires a water molecule to pick up the H to form H3O+. So they're just kind of like leaving that out for simplicity's sake. But there's a water molecule accepting that H3O+. But this is a weak acid, because as we just said, for a weak substance, when it breaks apart, the resulting substances are not that stable. So if they come back together, they'll reform the original molecule. And since the original molecule is in charge, at any given moment, I'll only create a few actual charges in solution. And so I'll only be able to conduct a small amount of electricity with that one.
Methanol, CH3OH, does not dissociate into ions when dissolved in water. It is a non-electrolyte.
So the number of methanol molecules that break apart in this solution, if I add the methanol,
negative charge, and the hydrogen has a partial positive charge.
So when the methanol mixes,
Fuel will break the attractions between methanol molecules, causing methanol.
Separate the methanols from one another. They're not breaking up. So I could imagine the methanol losing this hydrogen, and it will do that, but the number of molecules that will do that in solution is almost zero. So it doesn't affect the conductivity to a measurable amount. So this is a non-electrolyte because the molecule sticks together. So when I have the methanol, I don't get any ions, any measurable amount of ions. In water, I just have the methanol substance, and that substance stays together. It mixes with the water molecules, you can see them coming in.
To dissolve in water. Note that upon dissolving, the covalent methanol molecules remain intact. Compare this to the dissolution of an ionic compound such as sodium chloride, NaCl, which breaks apart into its component ions in water.
Because it's not forming charges, it's not going to be an electrolyte. So I don't have it conducting any electricity. Any questions about that? All right, let's take a short break. and then we'll finish that up and have the rest of the time for lapping.